So ready to get going? So ready to get going? So we're practically done with this, with chapter 29. So we're going to talk shortly about Heisenberg uncertainty principle. And after that, we'll solve the two problems on the board, and then we're ready to go with the new material, with chapter 30 and chapter 31 eventually next week. We have finished the chapter. The test is graded. You can pick it up after class. It is actually very good. We have a large number of people that did very well. So basically, everybody that has a grade of the order of 80, this is practically an A, because we have common questions that people practically do 100%, and we have brownie points. So 80% is an A, and this is a good thing. We have probably about, well, most of the class did actually very well. Which means that either the test was too easy, was it? It was, I think.
I think it was perfect, like a good balance between.
So how do you explain that we have a very high average for this one?
Studied hard.
You studied hard?
Yeah.
Or the test was easy, or my teaching was exceptionally good, I guess. Yeah, let's go with that. So look, now let's see what we have so far. So far in chapter 29, we are basically describing the basic results from quantum mechanics. And you start with wave-particle duality. So you basically say that, well, any wave can be interpreted as a stream of particles, and vice versa. A stream of particles always can be considered as a wave. So including this piece of chalk. So this piece of chalk clearly is a particle, at least it looks like a particle, but according to the rules of quantum mechanics, it also can be considered as a wave. Well, if you think about this piece of chalk as a wave, what is its wavelength? What is its frequency? Well, the wavelength is given with a simple equation which says that the wavelength of any object is equal to the Planck's constant divided by the linear momentum of that object, the magnitude of that linear momentum. So remember that linear momentum is defined just as a product of mass and velocity of the object. So using this de Broglie formula for wavelength, you can predict that piece of a stream of pieces of chalk thrown against opening with appropriate size is going to result in a diffraction pattern, just like the diffraction pattern from electromagnetic waves. Okay, so after that, we talked about the explanation for the black body radiation spectrum. So basically, it is again a story that started in early 20th century, when people tried to figure out what would be the color of the light emitted by a hot object, or object at temperature above absolute zero. And the only way to explain, to reproduce the spectrum of an object that is radiating due to its non-zero temperature is by assuming that this object emits light, but this light has to be interpreted as a stream of particles. Each of those particles has energy equal to Planck's constant multiplied by the frequency of the appropriate electromagnetic wave. So to explain the entire spectrum, you have to figure out, well, not figure out, but allow all possible frequencies and explain the total energy emitted by an object as a sum of photons. Each of those photons carries this amount of energy. So pretty simple explanation, but the arithmetic can be quite complicated if you want to do it properly. Well, so this explanation practically allows you to consider electromagnetic waves as a stream of particles, which this energy, each particle carrying this energy. And the last section of chapter 30 describes another peculiar property, peculiar prediction of the quantum mechanics after it was completely developed. And it is a prediction that if you know the location, the position of an object with certain accuracy, you cannot have infinite accuracy of measurement or knowing of the momentum of that object. So how it works? Look, the argument given in the textbook is very simple. So imagine that you have a single slit, and let's say that you have a stream of objects here, particles, waves. Let's say you have a stream of electrons. So since electrons have properties also of a wave, on the screen, on a distant screen behind the slit, you're going to observe a typical interference pattern with a maximum, central maximum, and secondary maximum following it. Now, let's say that the size of this opening, the size of the width of this slit is delta x, or of the order of delta x. So the fact that an electron made it through this opening means that you practically measured, or you know, the location of this electron at the moment when it was going through the slit. And you know its position with accuracy delta x, because this is the width of the slit. Notice also that the incoming beam didn't have any momentum along the vertical axis. Or if you can never have zero momentum, it is zero within some accuracy, but in general, the momentum of those electrons along the vertical axis is negligibly small. But you don't know where an electron is located well before it reaches the opening. After it reaches the opening, you know the position with certain accuracy, but the electron can go this way or this way or this way. In other words, you don't know with high accuracy now the momentum, in which direction the object, the electron goes. So it is a trade-off, and using the rules of quantum mechanics, you can demonstrate that the uncertainty of your knowledge of the position in x direction multiplied by the uncertainty of your knowledge of the momentum, x component in this case, has to always be larger or at most equal to Planck's constant divided by 4 pi. So very often Planck's constant divided by 2 pi is denoted with h bar. So very often you can see this inequality written as h bar divided by 2. Here again, h bar is defined as h divided by 2 pi. So standard notations, just introducing them. So you have here different ways to think about the Heisenberg uncertainty principle. So some people can interpret this principle that as a result of the measuring process, the measuring procedure, measuring of the position affects the momentum of the object. This is one way to look at it. But probably more accurate way of interpreting Heisenberg uncertainty relation is to say that the knowledge of position with certain accuracy leads to inaccuracy of the knowledge of momentum and vice versa. Okay, so in a similar manner, you can write uncertainty relations for the other components, the y component of the position and the y component of the momentum, and similarly for the z components, you can write exactly the same thing. A slightly different way of thinking about uncertainty in terms of energy and the time interval. A similar relation can be derived using slightly different methods as the uncertainty of the knowledge of the energy of the object and the moment of time when this energy measurement has been done. So the uncertainty of the energy multiplied by the uncertainty of the time also has to be equal or larger than Planck's constant h bar divided by 2. So those are basically results of quantum mechanics. They are very counterintuitive. So what I'm telling you is that if you see exactly the location of this piece of chalk, you don't know which way and how fast this piece of chalk is moving. So this is very counterintuitive, but this is the way how the world works on microscopic level. Okay, any remarks and questions related with this before we go to examples? So you're going to discover, once you start working on the homework assignment of chapter 29, you're going to discover that the questions are very, very easy. So basically questions of this type, on the final exam, you're going to have them mostly as multiple choice questions. The only question that is more, not more difficult, but it requires more than one step to answer is the homework question about the owl looking at some object and how many photons are going through the pupil of the eye of an owl per second or something of that nature. This is one of the problems in the homework assignment, so pay attention to that problem. It's a problem that connects the intensity of the light with photon energy, and we can actually make this problem more interesting, let's say, if you're also asked, let's say, to figure out what is the electric field in this stream of photons. If you interpret the stream of photons as electromagnetic wave, what is the magnetic field of this electromagnetic wave? So you have a combination between questions treating the light as stream of particles and also as electromagnetic waves, the way we did it in chapter 26 or 24, maybe. The chapter which connects intensity with RMS value of the electric field or magnetic field. Okay, so knowing this, let's look at examples from the homework assignment, starting with problem number 11. Problem number 11. So again, the questions related with the fundamentals of quantum mechanics are pretty simple. They are basically one-step questions. So problem number 11 is pretty much like this. It says that, well, it reminds you that we demonstrated that the kinetic energy of ideal monoatomic gas is given with 3/2 kT times the number of atoms. Where K is the Boltzmann constant, they give you the value in SI units, and T is the absolute temperature of that gas. So you're asked to figure out the broad wavelength of a helium atom with given mass, of course, that has this average kinetic energy. So in a similar manner, they could have asked you about the broad wavelength of nitrogen molecule, let's say in this room. Very, very similar arithmetic is going to answer the same question. So let's see how to do it. Well, kinetic energy of any atom in ideal monoatomic gas is given with 3/2 kT, the temperature of this gas. But on the other hand, you also know the definition for kinetic energy. It is 1/2 the mass of the object times its velocity squared. So here clearly velocity, we mean RMS value of velocity. So from this expression, everything is known except the RMS value of velocity, and you can calculate it. So from here you have 3/2 kT is 1/2 mv squared. You cancel the two, you solve for the velocity, and you have that average value, RMS velocity is equal to square root of 3 kT divided by the mass of your helium atom. So this is the average RMS velocity of the helium atom that has temperature T. So from here you can say that the magnitude of momentum, average linear momentum of this atom, which is of course the mass of the atom multiplied by V. So when you multiply this expression with M, you can write it all as 3 kT times the mass under square root, like this, after you cancel 1 power of the mass under the square root. And now, once you know the magnitude of the average linear momentum of helium atoms, you can immediately say that the corresponding wavelength is h divided by this linear momentum. In other words, you have Boltzmann, you have Planck's constant divided by square root of 3 times Boltzmann constant times temperature times the mass. And well, this should be the answer. The only difficulty in this problem is that you have to be careful when you're working with the calculator, because many of the numbers in this formula are small numbers. So you have to use scientific notations, and your calculator has to provide scientific notations rather than multiple zeros after the decimal point. Okay? Let's see remarks and questions. So when you plug in the numbers, look what is the answer? You're getting an answer of the order of 10 to the negative 10 meters for the wavelength of a helium atom at room temperature. What is the size of an atom? The order of magnitude. The order of magnitude of the size of an atom is also the same order of magnitude, of the order of 10 to the negative 10 meters. So the wavelength of an atom is of the same order as its size. Okay. Remarks, questions, issues here? Now, let's do the next problem, problem number 12. Again, from the homework assignment. So in this problem, again, there is a little bit of discrepancy between what they say in the first sentence of the problem and what they say in the second sentence. A little bit of discrepancy in the sense that the uncertainty of the position of an oxygen molecule has to be about half of the size of the alveoli. It's roughly half, but not exactly. So probably this problem could have been changed and made a little bit more reasonable by saying that the uncertainty of the position is 0.115, exactly half of the, or 0.11, exactly half of the size of the alveoli. Like this, it should be more reasonable. But the way you use Heisenberg uncertainty equations is by those equations give you inequality rather than exact equality. So rounding up numbers is, within some limits, is something that you can always do. So here, practically what they're telling you is that the uncertainty of the X position, let's say, of the oxygen molecule is 0.12 millimeters. 0.12 times 10 to the negative 3 meters. Right, you want to work in SI units in order to get the answer also in SI units. The question is, what is the uncertainty of the velocity? Well, you know that delta x times delta p has to be larger or equal to h bar divided by 2. In other words, the uncertainty of the momentum is h bar divided by 2 times delta x. This is the minimum uncertainty. And this is what they are asking for. So I am going into, from inequality, I'm writing the extreme size of this inequality. And after that, since linear momentum is a product of mass times velocity, this can be written this way. h bar divided by 2 times delta x. And the mass of an oxygen molecule is a constant. So you can write it out of this delta, and you have m times delta v x component is equal to h bar divided by 2 times delta x. And finally, the conclusion finally is that the uncertainty of the velocity, in this case, x component of velocity, let's say, is equal to h bar divided by 2 times delta x times the mass of the oxygen molecule. So this is going to give you a rough estimate about the uncertainty that they're asking for. Of course, this is uncertainty of the x component of velocity, but this accuracy again is the accuracy of this answer is sufficient to satisfy Webb sign, and you don't need to figure out uncertainty of the y component of velocity and so on. And this is going to be sufficient to solve the problem. Again, Heisenberg uncertainty relations give you order of magnitude understanding about the quantities involved. They're not giving you exact answers. Okay, any remarks and issues here? So look, this problem could have been solved in 2 lines rather than multiple lines, but I wrote it in detail so that you to see how the reasoning goes in this type of problems. Okay. So remarks, questions, comments, anything? Yes?
So is delta P equal to delta MVX?
Yes. Well, look, so this is PX, strictly speaking, right? Because the uncertainty relations are for each component. But here, you're not, since you're not using exact numbers for the size of the alveoli, you're always within some range. This is why I didn't bother to write components, but strictly speaking, Heisenberg uncertainty relations are component by component. Well, so questions of this type, you're going to have them as multiple choice questions, and you're never going to have answer that is going to be, take into account the size of the uncertainty of each component, after that square them and take square root. And so it is always a calculation that is only order of magnitude calculation, which means that one answer is going to fit and the others are going to be completely off. Or maybe no answer is going to fit and you have to choose none of the above. Sometimes this happens too. Okay, if no other questions, let's look at the last problem. Problem number 13 from this assignment. In this problem, you're practically invited to use the energy time uncertainty relation. So they tell you that you have an object, a particle that lives a very short time interval. And they are practically telling you, figure out the best accuracy with which you can know the energy of that particle. Or the mass and energy in particle physics are interchangeable. So what you do is just say, you start with the uncertainty relation for energy time. This has to exceed h bar divided by 2 again. In other words, this means that your uncertainty of the knowledge of the energy of this particle has to be equal or exceeding h bar divided by 2 times the time interval. The time interval that this particle leaves is given. And after that, you have to know that all types of energy combined as a single energy can be represented as a product of the mass of this object multiplied by the speed of light squared, like this. And again, the speed of light is a fixed number, a constant, so it can be written out of the delta, and therefore you're going to get that the uncertainty of knowledge of the mass of this object has to be larger or equal to h bar divided by 2 times the time interval times the speed of light squared. So this is again, order of magnitude calculation, and practically they tell you that the mass of a short-living object is known within certain interval. You never know exactly the mass of an object. And basically, the shorter the lifespan of the object, the less accurately you know the mass of that object. So this piece of chalk has practically infinite lifespan, right? You can look at it for a very long time, and it is never going to disintegrate into dust or something. And therefore, you know the mass of this, you can figure out the mass of this object with very high accuracy because of its long lifespan. Okay, any remarks, any issues? Okay, so what should we do next? Should we talk about material from the next chapter? Or should I ask some questions from this chapter? Let me tell you about the first experiment that gave an idea about the structure of atoms. So this is the so-called Rutherford scattering experiment. And it was done, I think, late 19th, early 20th century. And it's a very simple experiment. So by that time, people had some idea that materials are made of atoms. And the question was, what is the size of an atom, average size of atoms, and do they have some structure? So by that time, people already knew about electrons, the presence of electrons, negatively charged particles. And the common opinion was that the atom is a mixture of negatively charged electrons and positively charged particles to make the atom electrically neutral. And we know that atoms are electrically neutral, so you just mix them together, and this makes an atom. To investigate the accuracy of this concept, Rutherford set up a very simple experiment. So he had a stream of alpha particles. So alpha particles are helium ions, completely ionized helium ions, So he used the stream of alpha particles from radioactive sources. And he directed this stream of alpha particles to a tin or a foil, very thin foil, made of whatever material you want. So probably at that time, aluminum was probably more expensive than gold. So he did the experiment with foil of gold. And look, if you know the mass density of gold and any other material, and from that mass density and the volume that the gold occupies, it is clear that for a very thin foil, most of the alpha particles, actually practically all of the alpha particles have to go through the foil practically without deflection. In reality, he observed that indeed, most of the alpha particles go through the foil without being deflected, but occasionally you see an alpha particle that is recoiled, not only deflected, but goes in opposite direction. So here you have a set of detectors that see all the alpha particles. So what Rutherford did was he did a statistical analysis of how many of the incoming alpha particles are deflected and at what angle they are deflected. And with a very nice calculation, he demonstrated that this can only happen if your foil is made of atoms that contain a nucleus that is positively charged with a size of the order of 10 to the negative 15 meters. Well, if the atoms of gold are made of positively charged nuclei, where do you have to put the electrons in order to make this electrically neutral? Well, he assumed and he hypothesized that the electrons are orbiting around this positively charged nucleus in a manner similar to the planets orbiting the sun. So this is the first model of the structure of that. So it was a big achievement in the sense that for the first time you have certain measurement of the size of the atom and the structure, some idea about the structure of atoms. But of course, this idea has substantial problems. And you can immediately say what the biggest problem is. You have an electron that is negatively charged, of course, and you have nucleus that is positively charged. What do? There is an attractive Coulomb force between them. And if you apply the rules of electrodynamics, the rules that we studied for the entire semester practically, you're going to discover that this orbiting electron is going to lose energy and eventually fall on the nucleus if you use the rules of standard electrodynamics. And you can even calculate how fast this electron is eventually going to fall on top of the nucleus. And depending upon what assumptions you make, you discover that the electrons are going to leave an average of the order of a millisecond orbiting. And after that, all of them have to fall on top of the nucleus, which clearly doesn't happen because nothing like this happens with this piece of chalk or foil or any material. So clearly, this is a problem. So the Rutherford scattering experiment indicates this, but the classical mechanics, the rules of classical electrodynamics predict that this type of atom would be unstable and cannot exist for substantial time interval. So what do you do when you encounter a contradiction of this type? What do you do usually? So when you're solving some problem, and you encounter a contradiction like 5 is equal to 7 or some other problem that doesn't make much sense, what do you do? What do you do? Or you always have the problems right the first time? Okay, is there anybody that makes mistakes from time to time? What do you do?
You rethink the problem and start over again? You try a new experiment?
Yeah, well, people actually did exactly that. They checked the calculations, they repeated the experiment multiple times, the result was the same. Well, in mathematics, actually, you have a nice trick. So when you encounter something that you cannot prove, but it seems to be correct. In mathematics, in the history of mathematics, there are examples like that. For example, Fermat's theorem, Fermat's big theorem was not proven for centuries, but it was assumed to be accurate. It was proven actually recently. But when you encounter something that you cannot prove, you accept it as an axiom, as something that is accurate, and you start building on this axiom to see if you're going to encounter other contradictions. So immediately after the planetary model of the atom was formulated, people said, okay, it looks like atoms are stable. So even though classically an orbiting electron has to spiral down and fall on top of the nucleus, there are some orbits that are stable, and this doesn't happen. So it was just a wild assumption. So basically it indicates, well, the electron is allowed to orbit this way at this distance, or at this distance, or at some other distance, but not anywhere between them. And it looks like this assumption worked. So eventually, this assumption was tested using spectroscopy, and it led to the development of quantum mechanics. So it led to discovery of a simple equation that describes probabilistically the behavior of an electron in the electric field of a nucleus. So the result of this development, which actually happened quite fast, which in 10 years, people figured out how the things work, at least for hydrogen atom, for the simplest atom. And they predicted that the state of an electron in a hydrogen-like atom can be described using 4 quantum numbers. So the first quantum number that is needed to describe the state of an electron in hydrogen and similar atoms is called principal quantum number, and it can have only integer, non-zero integer values. The energy of each electron in hydrogen-like atom is given with a simple formula for hydrogen, it is 13.6 divided by n squared, where n, of course, is this integer number, and the energy, this formula gives you the energy in electron volts. Remember, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So, this expression for hydrogen atom tells you that the energy an electron can have in hydrogen atom is either 13.6 or 13.6 divided by 4 or 13.6 divided by 9 and so on. And you can go in the lab and check this formula. Right? So this formula basically tells you electron is either with this energy, 13.6 electron volts with 10%, or 13.6 divided by 4, which is, what is it? 13 divided, it's probably 3 point something electron volts, or it could be 13.6 divided by 9. Those are predictions, and you can easily check them by studying the spectrum of hydrogen. So if you take a sample of hydrogen and excite the electrons, excite the atoms so the electrons start, let's say, reach this level by heating up this hydrogen or passing electric current or something violent, do something violent with this hydrogen, so that you populate those high energy levels. Eventually, high energy levels are unstable. Eventually, the electron is going to skip back, let's say here, emitting energy in a form of electromagnetic radiation, in a form of a photon. And the energy of this emitted photon has to be exactly the difference between 13.6 and 13.6 divided by 9. No other energies of the photon are allowed. And indeed, the experiment showed exactly like this, exactly this type of spectral line, emission spectral line in hydrogen atoms. So, electrons that are located, that are with energy 13.6, those are the, you can demonstrate that those electrons have probability distribution, so they can live around the nucleus, roughly in a spherical probability distribution. So there is some probability the electron is here or here or here in a spherically symmetric manner. In a similar manner, you can describe the state of the electrons with that have principal quantum number 2 and 3 and so on. So we're going to stop here, and next time I'm going to talk about the other 3 quantum numbers that are necessary to completely describe the state of an electron in hydrogen or hydrogen-like atoms. So we're roughly going to be able to cover the basics of chapter 30 on Monday, and the remaining 2 classes next week are going to be on chapter 31. The goal is to put the foundations to be able to describe carbon dating, how carbon dating is done. So this is coming for next week. Don't forget the homework assignment is due tonight. Yes?
My number 13 is not working out.
So problem number 13. Okay, it should work out. It cannot. Okay, if you.
Work out for me.
Okay, if it doesn't work for you, come to the office and we're going to check your version and see what is happening. You may need some additional significant figures in your arithmetic. but it should work out. So if you're free, just stop. Let's do it in my office, and it should work. There is no way around.
Exactly.